Dear student, we are on the CEC Gurukul lectures. In today's lecture, we are discussing about the Hall effect experiment. Hall effect experiment, up to now we have discussed what is the Hall effect, what is the principle behind the Hall effect, what is the theory behind the Hall effect, and what is the apparatus we use in the Hall effect, and what is the procedure of the Hall effect. Now we will concentrate on the formula use, observation table, precautions, and what are the application of this experiment. So we know from the objective that what we are finding by using this experiment. We are finding the Hall voltage, we are finding the Hall coefficient, concentration of charge carriers, and mobility of charge carriers, and we are also finding the Hall angle. So this is very important, that we are finding the Hall coefficient by using this experiment, that is defined by RH, which is equal to VH, that is the Hall voltage, into T. T is the thickness of the specimen, Ix the current we are passing to the specimen, and By, which is the magnetic field, which is constant. And then we can, by calculating these all values, we can find out the Hall coefficient, and the unit of this Hall coefficient is centimeter cube per coulomb. So this formula is used to calculate the Hall coefficient. So already we discussed that we change the Ix. By changing the Ix, the VH will change, that we note in the observation table. Thickness is fixed of the specimen, which is already given, and By is the magnetic field, which is also constant, or we keep it as a constant value, that is 1500 Gauss. Now magnetic induction we can find out, that is the By, which is equal to VHT by Ix and RH. So magnetic field, that is in the Gauss, we can find out by this experiment. As we know RH, then we can find out By. So this experiment is used to find out the Hall coefficient, Hall voltage. Then here we know that VH is the Hall voltage developed between the upper and the lower faces of the specimen, because the moment of the charge carriers when the force is applied to the current carrying conductor in terms of the magnetic field. Then Ix is the current sent through the specimen, it is in ampere, and T is the thickness of the specimen, and the distance between the side faces and centimeter. Now we consider a uniform thickness semiconductor or a metal strip specimen placed with its length parallel to the x-axis. Now at this specimen, the current Ix is passed through this conductor along the x-axis. It means our specimen is along the x-axis and we pass the current along the x-axis. Now magnetic field By is applied along the y-axis. Then the charge carrier experiences a force, that is F, which is perpendicular to the XY plane, that is along the z-axis, as per the Fleming's left hand rule. And because of that, these potential voltage developed, that is the Hall voltage, because of this force which is experienced by the charge carriers. If the electrons are charge carriers, they accumulate at the upper surface. This surface acquires the negative charge, while the lower surface gets the positive charge. As the forces apply, all the positive or the negative charges will accumulate at the upper and the holes at the lower surface and get positive charges. Lower surface consists of the positive charges, and some potential differences developed between these two surfaces, and this is the electrostatic field, and that is the Hall voltage. This voltage is the Hall voltage, and the electric field is called the Hall electric field, that is represented by EH, and the Hall voltage is represented by VH. Now here we know that EF and EH, F means force which is applied, EH is the Hall electric field, then act in the opposite direction, that is the force due to the magnetic field, and the electrostatic field on the charge carrier acts in the opposite direction. So the net force on the charge carriers become 0. Here we see a slab which is connected with the VH we connected with the current, where we on the left hand side you are seeing that IX current is supply, then VH is developed at Z axis, and at the y axis magnetic field is applied. On the left hand side we see the current, magnetic field B along the y axis, and the potential difference VH developed along the Z axis. But here we see that F and EH are in the opposite direction. Now from this equation we know that Q VD cross BY plus QEH is equal to 0, or VD into BY plus EH is equal to 0, where VD is the drift velocity of the charge carrier, that is equal to J by NQ, where J is the current density, Q is the charge of the carriers, and number of the charge carriers per centimeter cube. That another physical quantity, that is RH, that is called the Hall coefficient, which is equal to the reciprocal of the amount of charge per unit volume, that is represented by RH is equal to 1 by NE. So Hall coefficient RH is equal to 1 by NE. E we require for the charge carrier electrons, and H for the holes, and here we represented by the charge carriers by the Q. So RH is equal to 1 by NQ, which is equal to EH by JBY. J is the current, E is the electric field, and BY is the magnetic field. So which is equal to VH by D, 1 by IX by A, and BY. We put the value of J here. So RH is equal to VH by D into 1 by IX by TD into BY, and ultimately we get RH is equal to VHT by IX BY, where it is the thickness of the specimen, D is the height of the specimen, A is the area of cross section of the specimen. So we can find out, and the charge carrier density we can find out by using the N is equal to 1 by Q, number of charge carriers, RH. If we calculate the Hall coefficient RH, we can calculate the charge carrier density by using this formula, N is equal to 1 by QRH. And if the conducting is primarily due to the one type of the charge carriers, then the conductivity related to the mobility is defined by mu m, which is equal to sigma RH, or we can write it as mu m is equal to R by rho. Rho is the resistivity. So we can find out RH, we can find out N, charge carrier density, we can find out the mobility by using formula mu m is equal to R by rho. Therefore another interesting thing, we can find out the Hall angle, which is defined by tangent theta h is equal to EH by EX. Hall voltage developed, current density because of the Hall voltage, and current density, the current passed through the specimen. So EH is equal to Vx into B. By putting this value, as we know that V x by Ex is equal to mobility, so tangent theta h means Hall angle can be determined if we know the mobility of charge carriers. So tangent theta is equal to mu m into B, magnetic field applied. So this experiment can be used to find out the nature of charge carrier. What are the output of this experiment? We can find out the nature of the charge carriers, means charge carriers which produce a Hall voltage may be negative when the electrons participated in it, it is positive when the holes participated in it. So the nature of charge carrier, minus or positive hole or electrons. Second, Hall voltage, that is a VH, by changing the current and place in the magnetic field, the specimen will generate the Hall voltage. So we can find out the Hall voltage, current through the specimen, how much current we are passing, and along this current we can find out the voltage of the current passed through the specimen. Then next is the applied magnetic field, conductivity of the conductor, but for the present it is confined to measure the unknown magnetic field also. Now in the observation, these values are fixed as the specimen supplied by the vendor. So these already mentioned, width of the specimen approximately 4 millimeter, length of the specimen 6 millimeter, thickness T is equal to 0.5 mm, and magnetic flux density that we will fix through the Gauss meter, which is B is equal to 3600 Gauss, and if we convert it into Tesla, then 3600 10 to the power minus 4 Tesla. This is the observation table we require when we are taking the reading. So first we did the serial number, then current, which measured in the milliampere, reading of the millivolt meter, that is MV, and in the one direction, and the second the third column is the reading of the millivolt meter in the reverse direction, V and I, and it is in the millivolt. After that, the mean value of the VH whole voltage, that is in millivolt, then we find out VH by I. We divide the whole voltage with the current supply. So VH by I in ohms, that is R, we can find out. So these are the observation table we require to note down the reading in the experiment. Now after getting the reading, we just plot a graph between the whole voltage and the current supply. After setup, the whole voltage is measured as a function of current keeping magnetic field constant and magnetic field keeping current constant, and this graph we get the straight line and then get the slope of this graph, and then we can put this value of VH by Ix in the formula to calculate the RH Hall coefficient. In the second table, which is for the table of resistivity, where we note down the current, we note down the voltage across this current, then we can find out the rho, which is Vx by I. So this is the table of resistivity. Now in the calculation, the mean value of Vh by I, that is 1.75 ohm. Then we will put this VH by I, the mean value we can take from the slope from the graph, and that is 1.73 ohm. Then RH is equal to VH by Ix into T by B. T is the thickness already given, and then B 15, and then we can 1500 ohm, and then we can find out the RH here. The sign on Hall coefficient is positive, the semiconductor crystal is of the P type. If it is negative, then the N type semiconductor. If we know the type of, first we know about it as germanium, what type of charge carrier we require. So to check whether the crystal is P type or N type, we have to first use the crystal of known type. Then after that unknown crystal we can put in this, and we can find out the Hall coefficient or the charge carriers. If it is positive, then the holes, negative for the N types. Now the N concentration we can find out, we put the value, and N is equal to 1 by Q into RH. Q 1.6 10 to the power minus 19 to RH, we put the value of RH, then 22.6 10 to the power 21 meter minus Q, then 5 rho. Resistivity we can find out, that is 0.107 ohm meter. Then mu is the mobility, that RH by rho, we put this value, and here the value will be 2.2 10 to the power minus 2, and whole angle, that is theta h. So we can find out the whole angle also. What is the conclusion of this experiment? Hall coefficient can be determined, which by using the RH is equal to VB by IH, and Hall effect can be used to determine the sign of the current carriers in the metal and in the semiconductors. So first we keep the known semiconductor, after that unknown semiconductor can be put, and the Hall coefficient and other parameters we can find out of that unknown semiconductor. A straight graph between the Hall voltage and the current between the Hall voltage, the magnetic field confirm their linear relationship. There is a linear relationship between the current and the voltage. Current which is passed through the conductor plus the Hall voltage. This point has important meaning, as Hall effect can be effectively used to determine the current or the magnetic field when other is known. So, and what are the precautions we have to keep in mind to perform this experiment? Number one is the Hall voltage should be measured very carefully and accurately. We adjust for the zero error. Second, the distance between the pole pieces of the electromagnet should not be changed during the whole experiment, and also the magnetic field should be the same through the experiment, through the one set of the experiment. Third is the current passing through the semiconductor slab should be strictly within the permissible limit, so that the voltage can be generated it in terms of the milliampere and millivolt. And what are the applications of the Hall effect? They are the basic application of Hall effect, so that why we are using this experiment. Here Hall probes are often used as a as a magnetometer, that is to measure the magnetic field, or we can find out the material or the specimen is a semiconductor or not a semiconductor. So Hall probes are often used as a magnetometers, that is to measure the magnetic field or inspect the material such as tubing in the pipeline using the principle of magnetic flux linkage. Hall effect devices produce a very low signal level and thus require amplification. Other applications are Hall effect devices produce a very low signal level and thus require the amplification. So in 20th century, vacuum tube amplifiers were expensive and unreliable, but with the development of the low cost integrated circuit, the Hall effect sensor became suitable for the mass application for the detection of the leakage. And this Hall effect is used to get the current sensor. So Hall effect current sensors are used in the integrated circuit amplifier to create a non-contacting current sensors. This has several advantages. No additional resistance or the shunt needed to insert in the primary circuit if we use this current sensors. Also the voltage present on the line to be sensed is not transmitted to the sensor, which enhances the safety of the measuring equipment. So these are used, these sensors are used, and this experiment, this Hall effect is used in this electric motor control also. Some type of brushless DC electric motors use Hall effect sensor to detect the positioning of the rotor and feed that information to the motor control. This type of Hall effect sensors are used to control the motors, and this allows a more precise motor control. On the left hand side we are seeing inside the motor, and that the motor can sense, and there are the positioning and the feed that information that we can get through this sensor. Next is the magnetometer. On the screen we are seeing that this type of magnetometer we can use. This is a smartphone like iPhone 3Gs are equipped with the magnetic compass, and this compass measures the Earth's magnetic field using the 3-axis magnetometer. Previously we used the galvanometer, nowadays we use the sensors, and these sensors we can develop by using the Hall effect sensors. These compass measure the Earth's magnetic field using the 3-axis electromagnet. These electromagnets are the sensors based on the Hall effect, and these sensors produce a voltage proportional to the applied magnetic field and sense polarity. These sensors can be adjusted by changing the voltage, and this voltage proportional to the how we can change by changing the magnetic field. Here we can change the magnetic field, so voltage can be changed, and the sense polarity also can be measured by using this magnetometer. Now, and there are many applications of the Hall effect, like these are used to find out the various experiment, like in the laboratory we can find out the type of semiconductor which you are using. We can measure the what type of charge carrier in the specimen and how much concentration of this specimen. Sometimes we prepare the semiconductor in the laboratory, and these semiconductors can be used for the measurement of the magnetic field induction also in this semiconductor devices. And we can use this semiconductor for the further for the electric devices. So the semiconductor developed, the intrinsic or extrinsic two type of semiconductor we use, but by using this experiment we can find out the parameters of the intrinsic semiconductor. Intrinsic semiconductors are pure type of semiconductor where no impurities are added. So Hall effect, in the Hall effect we use a pure type of semiconductor, and the Hall coefficient and the concentration and the type of charge carrier, moreover we can find out the how we can use this semiconductor in the sensors. What is the effect of magnetic field on the RH? There are the many questions related to this Hall effect experiment, like in the Viva voice we can have what is the Hall effect. Then we can say that when the electric charge conductor is placed in a semiconductor, is placed in the magnetic field, then the potential is developed which is perpendicular to the magnetic field and the current, and that potential is known as the Hall voltage. Another, we can ask a question like that, what type of the semiconductor we use to find out the Hall coefficient. By using this experiment we can use the intrinsic semiconductor, which are a pure semiconductor. And other experiment, what is the effect of the magnetic field on this semiconductor? The semiconductor will change its property, or the voltage will change when the current will change. So we can say that the magnetic field changes, the charge carrier will change. Next, we can find out that what is the linearity between the current pass and the voltage we are getting. So we can get a linear graph between the current we are supplying to the semiconductor and the potential developed, that is the Hall voltage. So there is a linearity between the change in the current and the development of the voltage. So, and what are the application of the Hall effect? By Hall effect we can produce a Hall sensors, Hall effect sensor, that must be used in the many devices, like to measure the earth magnetic field, to as a sensor we can use this semiconductor, and we can find out the many application of this experiment. So the Hall effect is the experiment where this is under the electromagnetic theory, and sometimes we can find out the charge carriers negative, sometimes we can find out the charge carrier positive. If the positive, then Hall concentration is there, and if it is negative, then the electron concentration is there. If we say RH is equal to minus 1 by NE, NE for it means electrons are participated in the development of the Hall voltage. Similarly, if it is in the RH in the plus sign 1 by NH, then it is the Hall, which is used to produce the Hall coefficient. So this Hall effect is used to find out the Hall coefficient. It is used to find out the Hall voltage. Moreover, Hall voltage, as well as we can find out the number of charge carriers, moreover type of charge carriers, and finally we can find out the mobility of the charge carriers, and then we can find, if we know the mobility of charge carrier, we can find out the Hall angle of these charge carriers, and the number concentration as we increase the concentration. How we increase the concentration of the charge carriers? We can ask a question in the Viva, how we can increase the concentration of the charge carriers, and how can we increase the voltage, but we keep the current in such a manner so that we can get the voltage in millivolt. So we supply the millivolt. We can increase the concentration of charge carrier by increasing the current supply to the semiconductor. So charge carrier concentration will increase, and then the potential we can get. So this we can find out the Hall coefficient, charge carriers. We can find out others parameters also, and this is the Hall effect experiment. Thank you very much.